Okay, and after you've solved a few problems, you will be able to see it, very, very quickly. So the non-Cartesian coordinate system that we're going to discuss first is called tangent normal coordinate system. Okay, so tangent normal coordinate system is particularly useful when the problems you're given radius of curvature information, you're given the speed, and you're trying to relate the two things in some ways. Okay, so let's say we have a curved path like this. All right, and on a curved path, this particular p has a velocity. Okay, so this velocity is given as v. Okay, we know that this velocity is always tangent to the path, right? So what we'll do is we'll say, okay, at this point p, we can create a unit vector which we'll call et sub hat, because it's a tangent vector and it's a unit vector. So we'll write we'll put the hat on top to indicate it's actually a unit vector. So we will create a unit vector that is always tangent to the path, right? So at point P, this is how it is pointing at point, let's say P prime over here. This is the velocity direction, and ET hat is still pointing in this direction. But clearly, the direction of ET has changed, right? Going from P to P prime. So this is P prime, this is the velocity V prime, and over here, this is really ET hat prime, right? So your tangent vector is your tangent vector is changing, and as a result, your unit vector pointing along the tangent direction is also changing. Okay. Then we will also create another vector, another unit vector, which will be perpendicular to ET hat and is always going to point towards the concave section of the path. Okay, and we've already seen that if, let's say, a particle is moving along a curved path, and even if its speed is same, if the magnitude of the velocity doesn't change, it still has an acceleration component that points towards the concave direction of the path, right? So we will say, okay, we will create a vector which will be a unit vector perpendicular to the tangent direction pointing towards the concave side. So this angle over here is 90 degree. So at this point, at point P prime, if I ask you what is the direction of the tangent vector, assuming that this is really turning like this, then En hat is pointing that way. If you get over here, Et hat is tangent and En hat is pointing towards the concave side. Or you can say that you can draw your kissing or oscillating circle at every point, and the En hat would be actually pointing towards the center of that circle. So at point P, this is your circle that you can fit, and this is the center, and En hat is pointing towards the center. At point P prime, here is your circle, and En hat is pointing towards the center. Again, at this point, you again fit a circle, and En hat is pointing towards the center of the circle. Okay, so Et hat and En hat are always perpendicular. So Et hat is always perpendicular to En hat. Okay, Et hat is points towards the tangent direction, and En hat points towards the concave direction, or towards the center of the circle that you can fit at a particular point along that path. Okay, all right, so let's do some math. So we're starting with information about the velocity. So velocity is given as it's a speed or the magnitude and a unit vector pointing along that direction, right? So that's our starting point. So what is acceleration? Well, acceleration is defined as dv over dt, right? That definition is still valid. So d over dt of v et hat. And what is that? So this is a product of two functions. So v is one function, right? And et hat is the second function. So first function, second function. Okay, so if you're taking derivative product of two function, what is that value? Is dv over dt times et hat plus v times d over dt of et hat. So essentially the derivative distributes through the product of two functions, right? Okay, so dv over dt, what is that quantity? Well, we know what this is. This is essentially telling you what is the change in the speed, right? So you're driving at 55 miles an hour, next moment you're driving at 60 miles an hour, next moment you're driving 65 miles an hour. Clearly your speed is changing. And essentially this term tells you something about the change in speed over time, right? Now let's look at this term, d over dt of et hat. What is d over dt of et hat? This is telling you what is a change in unit vector along tangent direction over time. What is changing about this unit vector? Is the magnitude of the unit vector changing? No, by definition it's always unit magnitude, but or But what about the direction? Is the direction of et hat changing? Yes. So if you look at this particular case, you can see that et hat is pointing this way here, et hat is pointing this way here, et hat is pointing this way over here, and clearly this quantity is not going to be zero in general because et hat is changing direction. So then that begets the question, what is this quantity, right? It is basically the derivative of a unit vector. Now, derivative of a unit vector is actually something that we will need time and again in this class. So let's look at that. So let's do this. Derivative of a unit vector. Okay, so let's say we have a unit vector u hat, okay, which means that magnitude of u hat is actually equal to 1, right? And we're looking at the derivative of unit vector u hat. So d over dt of u hat. What is this quantity, right? First of all, let's look at this. U hat is a unit vector, which means I can write u hat dot u hat equal to 1, right? If I take the derivative of this equation, what do I get? The right hand side would be 0, and the left hand side would be u hat dot d over dt of u hat plus u hat derivative times equal to 0. Sorry, not times, but dot equal to 0. And both of these terms are same because a dot b is equal to b dot a. So what we get is u hat dot d over dt of u hat equal to 0. Now this is actually pretty, useful because this is telling us that the derivative of a unit vector, which is this quantity d over dt of u hat, is perpendicular to u hat. Because if a dot b, the two vectors a and b are dotted and the result is 0, unless a and b are trivially 0, either of them, then we know that they're perpendicular to each other, right? So what this is implying is that d over dt of u hat is perpendicular to u hat. Now if you have a unit vector and you can get two perpendiculars to it, right, if it is moving in a plane, right? So the question is which way is exactly it is pointing. So let's get that. So if you have a unit vector, we know that a unit vector can be written as, let's say, cosine theta I hat plus sine theta j hat, where graphically I will show this unit vector as making angle theta from x-axis, okay? And clearly, the only thing that is changing about u hat is the theta, right? Its orientation. So essentially, it's going to be moving along a circle. The tip of this unit vector will be actually along a unit circle at all times, right? And it's clear that this is magnitude 1 because the square root of cosine square theta plus sine square theta is 1, right? Okay, so d over dt of u hat can be written as d over d theta of u hat times d theta over dt. So I need to bring theta over here because I have u hat given as a function of theta, right? Okay. So d theta over dt is theta dot. I'm going to bring it to the front. And I have d over d theta of u hat, which is nothing but cosine theta I hat plus sine theta j hat. Okay. So what is this? This is minus sine theta I hat plus cosine theta j hat. Okay. So we have theta dot over here, right? And we get that. Now, I can also write this in the following way. I can write this actually as theta dot k hat. So k hat is a unit vector which is perpendicular to the plane, right? So k hat is pointing perpendicular to the plane of this sheet, pointing upward, right? Because this is I hat, this is j hat, right? So, and I hat, j hat, and k hat, they form a right-handed system, coordinate system, right? So this can be written as theta dot k hat cross cosine theta I hat plus sine theta j hat. Okay, so let's look at this. So is this really true? So we have k cross I. What is k cross I? K cross I is j, and this is cosine theta, so we get basically this term. K cross j is minus I, so we get theta dot minus I times sine theta, which is this term. So both of these are essentially, same. So there's no problem with that, right? So what is this quantity? This is nothing but u hat itself. So this is actually theta dot k cross u, and that's nothing but u dot, right? That's the derivative of u. So what this is telling you is that you can obtain the derivative of a unit vector by taking a cross product of a vector that points in the positive k hat direction, and its magnitude is the rate of change of the angle, which is theta dot, and theta dot is nothing but the rate at which u hat is really rotating, right? So at the rate u hat is changing the direction. So if u hat was moving very fast, it was changing its direction very fast, then theta dot would be a very large quantity, right? You associate a direction with that vector, which we call, k hat. So we get theta dot k hat, and you cross it with the unit vector itself. And that's how you get the derivative of a unit vector. And this is a result that we will need a few times in this class. So I'll call it, a very important relationship. So now that we have seen how to obtain the derivative of a unit vector, let's go back to the relationship that we had for the acceleration in the tangent normal system, right? So let's rewrite this over here. So in the tangent normal system, the acceleration is dv over dt, which is v dot et hat plus d over dt of et hat, and v is outside over here, right? So v dot et hat plus v times derivative of a unit vector. And what is the derivative of a unit vector given as? By this relationship. So this is theta dot k cross the unit vector itself, right? Okay. So this is v dot et hat plus v theta dot k cross et. All right, so let's try to figure out what this relation k cross et is, right? So we know that et is a vector which is tangent to the path. En hat is another vector that we have postulated, which is perpendicular to En hat and points to towards the concave direction. And k hat is a unit vector that is actually perpendicular to the plane of travel of the path, right? So since we are dealing with only the motion in the xy plane, k hat is a unit vector perpendicular to the path, right? To perpendicular to the plane. So k cross et has to be equal to either positive en hat or negative en hat, right? It turns out that it is always going to be en hat. For the reason it'll become clear very soon. So let's say the particle is moving up like this, right? So here it is at point P, and that's the et hat over here, and then over here at point P prime is moving up. So this is et hat over here, right? So you can clearly see that the direction of the et hat is changing, and the angle it is making from horizontal, let's say this is the angle theta it is making from horizontal over here, and this is the angle theta it is making over here from horizontal, has changed, and it has actually increased, right? So what this is saying is that theta dot is positive. Okay, so theta dot is positive. The rate of change of angle is actually is increasing, is positive. So theta dot is positive. So in this case, k hat is actually pointing perpendicular to this plane upward. Okay, so it's pointing upward, right? And then you have k and you have et hat. So if you take the cross product of k and et at point P, this is going to be pointing towards the concave side, which we know is same as en hat, right? So k cross et hat is nothing but en hat in this case, and it's pointing towards the concave direction. So we get that. Now, what happens when et hat is actually changing its direction such that theta dot is negative? So that would happen if, let's say, something like this was happening. Here is point P, here is point P prime, this is et hat, and this is et hat over here, right? The angle it is making from horizontal theta is actually, decreasing, right? It's decreasing. So in this case, theta dot is actually negative, which means it's actually pointing into the plane of the travel of this path. Okay, and that means that when you take this cross product over here, theta dot is negative, so that will be actually minus k cross et hat, and that would give you the same direction as en hat towards the concave direction, right? So k cross et hat is always positive en hat. So what do we get as a result over here? This is v dot et hat plus v theta dot en hat. Okay, so we have the theta dot over here, but theta dot is not a very good quantity for us because we are really looking for a relationship between velocity and the radius of curvature. Okay, So let's see if we can change this. So v dot et hat remains. This is d over dt of theta, and en hat remains. D over dt of theta, what is that quantity? So let me write that separately. D theta over dt, why a change of variable can be written as d theta over ds times ds over dt. Okay, what's ds over dt? ds over dt is the velocity. So this is v d theta over ds. So it's not actually a velocity, it is, sorry, the speed, right? V theta over ds. This is nothing but v times, so do we know what d theta over ds is? This is v over radius of curvature. So ds over d theta in differential geometry is defined as the radius of curvature. Now you have used something similar for, something like a circle, right? If you have a circle, you have an arc subtended over here, let's say of this of distance delta s, then the angle that this arc makes at the center, let's call it delta theta. There is a relationship between these two, right? If the radius of curvature is rho, then delta s is rho times delta theta, right? So in the limit when delta theta goes to 0, you can write this as rho equal to delta s over delta theta, right? And in the limit when delta theta goes to 0, this becomes ds over d theta, right? And that's the relationship we are using over here, okay? So, this is not without a lot of rigor over here, but that's the general idea, okay? So ds over d theta is radius of curvature. So going back over here, this is now rho times d theta over, rho times, where is this? Oh, I already actually wrote this. Okay, so we have d theta over dt equal to v over rho. Okay, so let's write that here. V dot et hat plus v times v over rho, so that becomes v squared over rho times en hat. And that's your acceleration expression in tangent normal coordinate system. Now this is interesting because we are looking at the expression of acceleration in the tangent normal coordinate system, and it has two components, right? There's one component that's pointing along tangential direction, another component that's pointing towards normal direction, right? So I can write this a little bit differently. I will write this as acceleration along tangential direction unit vector et hat plus acceleration along normal direction unit vector en hat, right? Where at is the tangential component of the acceleration given by v dot, and an is the normal direction component of acceleration given by v squared over rho. Okay, so along a path at any given point, there is a tangent component which is at, right, which is given by v dot, and there is a normal component an, right, at any given point. And tangential direction acceleration is given by change in speed, right? So this is change in speed, and that's along the tangential direction. So if you're driving your car along a curved path and your speed is changing, there will be a component of acceleration along the direction of the tangent, which is same as the direction of velocity, right? And then you have a second component of acceleration, which is given as v squared over rho, and that is due to change in direction of velocity. That is due to change in direction of velocity. So if the velocity direction is changing, you will have a normal component of acceleration. Now you can see over here that even if v is constant, so even if v is constant, which means that speed is constant, acceleration is not going to be entirely zero. Why? Because acceleration is given as v dot et hat plus v squared over rho en hat, right? V dot would be 0 in this case because v is constant, but this is not 0 unless v is 0. So v squared over rho en. So unless v is 0 or radius of curvature is infinity, which will happen along a straight line path, the acceleration is not going to be 0, right? So going back, what are the terms that we need to compute the acceleration over here? We need the change in speed, we need the actual speed, and we need the radius of curvature, which is nothing but the radius of the circle that you can fit at the point where you're interested in computing the acceleration. So let's look at, couple of simple examples. So example one would be a particle moving along a circular path. Okay, so particle is moving along a circular path, and we want to know what's velocity, what is its acceleration. Okay, so let's say particle P is over here. Okay, and its velocity is given to you as constant v0. Could be something like, let's say, 5 meters per second. And the question is, what's its acceleration? Well, acceleration has two components in general. You have the tangent component and you have the normal component. Notice how normal component is pointing towards the center of the circle. So acceleration is v dot et hat plus v squared over rho en hat. Since v0 is constant, v dot is 0. So this is equal to 25 over rho. Let's say the radius of this is 1 meter over 1 en hat meters per second squared. So the only acceleration it has is the one that is pointing towards the center. And in physics, you have learned that this kind of acceleration, v squared over rho n, is called centripetal acceleration, right? Why? Because it points towards the center. Now, the direction of the centripetal acceleration continues to change as the particle is moving along the circular path, right? So if it's over here, it's pointing this way. If it's over here, it's pointing this way. If it's over here, it's pointing this way. Okay, and that's how the acceleration works. Another example is of a track which has, let's say, a straight line first and then a semicircular arc. Okay, and then it could follow further by a straight line, right? And let's say you have a railroad car traveling along this path. Okay, and it's moving at constant velocity. So it's moving at constant velocity over here. First of all, what's its acceleration when it is moving over this flat section, right? So at the flat section, so over flat section, what is the acceleration? Acceleration is, again, you can still employ the tangent normal system. So tangent normal system is applicable for curved path, but it's also applicable for a straight line path, right? So acceleration is equal to v dot et hat plus v squared over rho en hat, right? Now velocity is given to you as constant, which means that this term would be 0. Okay, so what about v squared over rho? Well, what is the value of the radius of curvature over the flat section? The rho is actually infinity, right? Because you will need a circle of infinite radius to fit over the flat section, which means that this quantity is also 0. So over the flat section, acceleration is 0 meters per second squared, right? And that is expected because you know from your analysis of a straight line motion that if velocity is constant, then acceleration is 0. Okay, so it's not like that you're using a tangent normal system, so the results are going to be any different, right? Okay, now let's say it gets onto this circular track. So it was at the flat section, and right after this line, it gets onto the curved section. So right after it crosses the flat section, it gets onto the semicircular arc. So let's say this is a semicircular arc of radius r. What is the acceleration? Well, acceleration would be equal to v dot et hat. I'll write this expression again, plus v squared over rho en hat, right? Now velocity is still, the speed is still constant, so this will be 0. But what is this acceleration now? It is v squared 25 over rho, whatever this r may be. Let's say this r is 2. So the value we get is 12.5 meters per second squared, pointing towards the normal direction. Now this is interesting because what has happened is that just before it got onto the curved tracks, in the flat section the acceleration was 0, but now all of a sudden there is an acceleration in 0 amount of time pointing towards the center. And this is going to lead to very unpleasant effects for the people traveling inside the railroad car. And that's the reason why you would never have this kind of thing, okay? So the tracks are never designed like this. If you have to design something like where you have to take a U-turn, which doesn't happen very often, of course, with the train tracks, it will be a very, very gradual change in radius of curvature so that people don't feel this sudden amount of change in acceleration, which gives rise to actually jerk. So there is a quantity called jerk, which is defined as rate of change of acceleration, right? We talked about the velocity defined as change in position over time. We talked about acceleration as change in velocity over time, but change of acceleration over time is defined as jerk.